Nelson, and I'm here to talk to you today about metadata privacy beyond tunneling for instant messaging. We also call this work DenIM, Deniable Instant Messaging. And this is joint work with Elena Pagnin and Aslan Askarov, and this is I'm generally funded here by the European Union. So let me start by setting the stage and talking to you about instant messaging. What are the rules here? So we are assuming some instant messaging apps such as WhatsApp, Signal, iMessage, Telegram that you might have on your phone or on your desktop device. And these messaging services usually come with some kind of message confidentiality, whether that's end-to-end encryption or just between device and server. That differs from different applications. But some of them actually use the very strong protocol called Signal, which gives you strong cryptographic guarantees through sort of maintaining freshness of the cryptographic keys used. But still, even though a lot of them use encryption to get you confidentiality, they don't give you metadata privacy. So Alice and Bob might be able to protect the content of their messages, but their metadata can still be obtained by Mallory. So I will show you what the setting looks like. So it's instant messaging, which means we will have a centralized server that forwards messages. When Alice wants to talk to Bob, this has to go through the server. So Mallory can actually, if she's able to observe the network layer, she can just observe this forward and learn that Alice talks to Bob without knowing anything about the message content. So this can be encrypted, but this still leaks as metadata. So this transport layer actually carries a bunch of metadata, like who talks to whom, when conversations happen, and how often people communicate. So it's possible for someone like Mallory to map out maybe the social networks of Alice and Bob just by observing transport layer data. And if Mallory is a strong attacker that's able to observe a big part of the network, she can just get a lot of data and then run traffic analysis on those, right? So you can automate the extraction of the metadata is my point. So what's the design space if we want to actually protect against this, if we want to give metadata privacy? So usually this area is also called anonymous communication. So there is this paper called the Anonymity Trilemma, and it maps out what we're allowed to achieve here, basically. So strong anonymity, low bandwidth overhead, low latency. These are all nice properties that we want, but in reality, we have to choose two. And this is from Oakland in 18. So I drew for you here what the trilemma looks like. I'm here using strong privacy instead of anonymity when talking about the same property. What we have seen in prior work is what I will tell you about, and also where we want to be in this trilemma. So we actually want to make sure we have strong privacy and make some sort of trade-off between bandwidth and latency, but never sacrificing privacy for the others. And the sort of competitors in this space, if you will, are what's called round-based protocols or DC networks, dining cryptographer networks. The idea here is that if you make all participants in the protocol, you just behave the same way. So they might send the same size message at a fixed point in time, all of them, just like having these rounds of send message. Whether you have something to say or not, you have to participate in each round. It's very nice because it's quite easy to show that you get privacy from this because everything looks the same, but it's very resource exhaustive and expensive to keep running. And if you all of a sudden stop sending messages, not only are you affecting the privacy for you, but also for the other people, because you actually shrink the anonymity set, you shrink the amount of people in the protocol that could have sent something. So these things are theoretically very good because they're strong in the privacy guarantee they give, but implementing them and actually running them in reality is too expensive, so we don't see them in the wild. On the other hand, we do see things in the rest of the design space, like the sort of more performance favoring protocols that do not have strong privacy. This is where most of the work is. And especially you might have heard of Tor, the Onion router. It lives in this design space. So it cannot offer strong privacy because actually there is a bunch of de-anonymization attacks against Tor. But it actually, unlike those others, it exists in the wild. So this is somehow the best we have so far. but we would, on the other hand, then like to put that stuff in that yellow space, right, to actually give strong privacy and also be feasible to run. So the idea is to open up a new trade-off from what we've seen before in this trilemma. So we're still constrained by the trilemma, but all of the applications there actually had a very ambitious goal, which is that they wanted to give metadata privacy to all of the messages all of the time. So what we're saying is, can we have some sort of hybrid message model instead, where let's give metadata privacy to some of the messages, like some of the time. So instead of every message is hidden, let's choose which messages we want to hide, and then mix these non-metadata private messages and metadata private messages in the same system. So a hybrid system. We will call these metadata private messages deniable, and we will make them piggyback on these regular non-metadata private messages. And I will show it like this. I will have these regular messages shown with a normal outline, and deniable will have this dashed outline. And when I say piggybacking, what do I mean? Well, I mean that we can chop up the deniable messages and piggyback them by putting them as a trailer on a regular message. And this also gives us another property that we actually we weren't aware of in the first place, that there's this thing called cute cat theory of censorship that gives censorship resilience. And so it's from a paper that's not in computer science called Cute Cats to the Rescue. And it actually tells you that these hybrid systems are beneficial if you want to have censorship resilience. So imagine that we have two systems, A and B, and then we have some secret content, like let's see some political content or something that we're worried might get censored. So if we also combine our sort of sensitive secret content with something like cute cats or memes or something else in the same system, we create a hybrid system, it's actually giving us better privacy because it's harder to censor. So imagine, for example, like this is, for example, Reddit, where there might be one of the subreddits that have something sensitive that could be blocked, but it also has all of these other subreddits, right, with like the memes and that other people go to. And if you were to just take down all of Reddit, there would be probably a public outlash saying, hey, we want our memes back, right? Whereas if you just take down this like very niche content that would be in system A, that's much easier to just like silence people, because at that point the rest of it doesn't have as big user base essentially. So system B is actually more censorship resilient, and this is what we also gain from our hybrid model. So now let me tell you about this DenIM, the Deniable Instant Messaging, and how it gives you metadata privacy and why it's beyond tunneling. So first of all, I guess you're wondering now, how strong is Mallory and what can she do? What's the threat model? So it's actually a strong attacker. She's active, global, external attacker. So by active, I mean that she's participating in the protocol. In our case, this is the Signal protocol, and so she can send messages to Alice and Bob and request keys from globally shared resources and so on. And she's global in the sense that she can observe the entire network, so see what's going on. And also importantly, she's an external attacker. This means she is not compromising Alice or Bob's devices or the centralized server that we actually rely on to do this sort of routing. So that's the attacker. And now let's look at what does the protocol actually look like when we run it. So again, we have the centralized server, remember, and we have Mallory trying to figure out if Alice is talking to Bob or not. So for example, we could have here that maybe Alice is a whistleblower and Bob is a journalist. So of course Alice doesn't want Mallory to find out that she's talking to Bob. So she wants to send this sensitive deniable message to Bob. So she will write that. And this might be like right before she does something else, or it can sit there on Alice's device for a while because we assume that won't be compromised. And then at some point, this is instant messaging, right? So Alice might want to talk to her friend Charlie, maybe saying, hey, Charlie, what's up? You want to go for coffee? And then we can chop up the deniable message for Bob, and we can actually forward that then to the server. So note here, right, that the deniable message for Bob is not forwarded to Charlie, it just reaches the server where it lies. Also important here is that you might say that, well, wouldn't Mallory see that the message from Alice to the server and then the server to Charlie looks different because the deniable part is now different, right? In one case it has the message for Bob, and in one case it has nothing. Well, there's also like a TLS encryption between Alice and the server and Charlie, so these messages will not look the same to Mallory, so she can't just simply trace them. Anyway, Alice and Charlotte have been talking, but now also enter Bob's friend Dorothy, who might be messaging Bob later. It might be like, immediately or days later, sort of doesn't matter conceptually. So she might be saying, hey Bob, how are you? Haven't talked to you in a while. And that actually helps us to push out the message from Alice to Bob, and such that Bob can then reconstruct it. And these messages, again, they don't have to be like right away in some sort of rapid fashion. It's just that we need these messages to push out the message, the deniable message. Okay, so what has Mallory learned from seeing this? Right? Before she could actually easily see that Alice and Bob are talking, at this point she has seen Alice was talking to Charlie, Dorothy was talking to Bob, but she's not seen any direct communication between Alice and Bob. So that's the idea. And so that seems very simple, right? Like, how hard can it be? Why don't we just like piggyback the thing and call it a day? Well, actually, there are some concepts here that we need to think about carefully. The first part being the chunking of this deniable message that we want to add. Like I said, we just chop it up, right? But we need to make sure that this deniable message is the exact length on the wire, on the network when we send it. So we assume that Mallory she will know how long this chunk should be, and we need to make sure it is exactly that size. And what's difficult here is actually when you serialize a message, there might be some optimization that causes the message to be not the length you wanted it to be. In our implementation, for example, we use a commonly used serialization library, Google's protobufs, and it uses variant encoding, which means that it creates some gaps to save some space. It creates some gaps, and it does not become the exact length that you want it to be all of the time. And this, of course, creates a side channel that we need to close. So one needs to be careful with the chunking. And I said that it's beyond tunneling. Why is it beyond tunneling? Why didn't we in the first place just pretend that this was all regular messaging, or we just pretended it's a different application? Like why did we have to go beyond tunneling? Well, remember that Mallory is an active participant of the protocol, and she can start like communicating with Alice and Bob, and she can request the keys and so on. And it turns out that if we then use regular signal, it does not give us metadata confidentiality, because there are certain leaks, there are certain attacks that Mallory can perform. We have them all in the full paper if you're interested in them. But so just taking regular signal and piggybacking that and that deniable part would not work. Basically because there are leaks on the application layer, which are possible for Mallory to observe because she is an active participant of the protocol. So what we have to do instead is develop a deniable version of the protocol. In this case, a deniable version of signal. So the contributions from our paper is, first of all, this deniable protocol, the deniable signal, which is an extension of the signal protocol, which means we inherit all the nice cryptographic properties of the signal protocol, and then we enhance it with also metadata privacy. We also construct a formal model of deniable signal, because we need to go beyond tunneling, right? We need to actually model what that protocol does. And then when we have modeled the protocol, we can actually prove privacy and provide a theorem that says that nothing leaks from deniable signal. And this property is actually called non-interference. It's quite standard to look at if you're from the field of information flow control. So basically, we will show, we prove that nothing from this deniable signal leaks into any of the channels for the regular signal. So that means in the protocol and in the network, any shared resources and so on. We actually prove that there is no such leakage. And we also have a proof of concept implementation, and that uses the open source version of Signal, which is also what's used in the Signal application, for example. So we do not reinvent the wheel by implementing any cryptographic libraries here. We reuse what's out there. And so this implementation is a TypeScript implementation, and we run it on Node.js. So we run it on a real network. We run some machines, we set up a server, and we run clients, and then we just simulate that we send messages between different clients and to push the system. So in this experimental setup, we also have empirical research questions that we answer. And first of all so how does this deniable traffic influence the performance of regular messages if we use different parameters and different behaviors? And this is basically to say, if Signal or WhatsApp were to implement this tomorrow, would their sort of regular their already existing app, would that be suffering a lot? Would people then have a lot of latency or something in their regular messages and maybe stop using the system because of it, right? So we're testing the feasibility here. And we do that for looking at server throughput, how many messages can we handle, and the end-to-end latency of delivering messages. We also are interested in the behavior of the deniable traffic, and especially how long does it stay on the server, because we don't want it to be an easy point for malware just to attack, right, with all of the messages just sitting waiting to be forwarded. So we look at the length of the buffers of deniable messages and also the end-to-end latency of deniable messages. So basically, what's the overhead? In this experimental setup, we are wanting to see sort of best performance of the system. So we push CPU utilization to like around 100%. And what we see here in the spikes are garbage collection that happens. That's also something we're sort of keeping it at the maximum capacity. And we have a bunch of results here as a plot with the latency for regular messages. As you can see, this is a log plot, so observe the axis, and I'm showing it for different proportions of regular to deniable messages. More of these plots are in the paper, but what I want to say here is that it's not a clear linear scale. Like essentially, when you go from no deniable messages to deniable messages, you pay more than you then pay for increasing the size of this padding that you have. And so in conclusion, what I've told you today is that metadata leaks on the transport layer, which is bad if you want to protect yourself against a strong adversary such as malware. I've also told you that the existing solutions are costly, or they give you weaker privacy than you might want. For example, if you use Tor, it can be de-anonymized. And this is because we all have to remain within this anonymity trilemma, and we try to favor strong privacy. We do this by introducing different message types to open up a new trade-off between these regular and deniable messages in the same system. And in this case, we have now reformulated privacy in anonymous communication as an information flow problem, which also means we can start using information flow techniques to solve this problem. And those techniques haven't been used in this area before. So the privacy guarantees in this paper is actually coming from proving non-interference between this regular and the deniable messages. And more details are in our paper, Metadata Privacy Beyond Tunneling for Instant Messaging. It's available for you online today. So thank you for listening to my talk, and I hope you look forward to reading the paper.